we're going to talk about nonlinear systems in three dimensions. First, let's review some ideas about dissipative systems. Recall that we began with the following motivating question. Let's consider the unforced harmonic oscillator. We can express this in the form dy dt equals a times y, where A is a 2 by 2 matrix in the form 0, 1, negative q, negative p. Here, p is in terms of b over m, where b is the damping coefficient, and q is k over m, where k is the spring constant. We found before that this system is a Hamiltonian system if and only if p is equal to 0. That is, our system is undamped. But how do we study this system for any p? That is, if p is not equal to 0. For the moment, let's say that p is arbitrary, and let's say that y of t, which is x of t comma y of t, is a solution to this system. We'll denote the total energy, that is E of t, as the sum of the potential and kinetic energies. The potential energy coming from the spring is 1/2 kx squared, and the kinetic energy is 1/2 my squared. If we take the derivative, that is, we compute dE dt, we find that this is less than or equal to 0. In other words, since the change of the energy is negative, this means the energy is being dissipated from the system. That is, energy is being lost when there is friction, when B does not equal to 0. More generally, say that we have a two-dimensional autonomous system, dx dt equals f of xy, and dy dt equals g of xy. We have three statements to make. First, there exists a function g, so that f is dg dx and lowercase g is dg dy, if and only if df dy equals lowercase dg dx. In this case, all solutions, capital Y of t, satisfy the following. dc dt is less than or equal to 0, where c of t equals negative g evaluated at this point, x of t comma y of t. Moreover, equilibrium points for such a system are either saddles, nodes, sinks, or sources. They are never spiral sinks, centers, or spiral sources. Any system satisfying these equivalent criteria is called a gradient system. Any function, L of xy, such that c of t, which we can write as L evaluated at x of t comma y of t, satisfies c prime is less than 0, is said to be a Lyapunov function. Intuitively, we think of L as a measure of the energy, such that this c of t is the energy at time t. Systems which have a Lyapunov function are called dissipative systems. Here's a motivating question. Can a two-dimensional autonomous system be both a Hamiltonian system and a gradient system? A Hamiltonian system means df dx equals negative dg dy, and the gradient system, as we just discussed, means df dy equals dg dx. This means the second partial of f with respect to x plus the second partial of f with respect to y equals 0. Such an equation is called Laplace's equation, and its solution f is called a harmonic function. Such an equation is an example of a partial differential equation. Today, we're going to discuss nonlinear systems in three dimensions. So let's return to three-dimensional systems. That is, we have dx dt equals f of t x y z, dy dt equals g of t x y z, and dz dt equals h of t x y and z. We'll say that this three-dimensional system is autonomous if the functions f, g, and h are not functions of time t. We say that a point x0, y0, z0 is an equilibrium point if f evaluated at this point is 0, g evaluated at this point is 0, and h evaluated at this point is 0. In this case, the constant function, capital Y of t, equals to this point, x0, y0, z0, is said to be an equilibrium solution. We've already seen three examples so far in this course of such an autonomous three-dimensional system where we've considered their equilibrium solutions. Let's start with the SIR model. Recall back in Lesson 16, we focused on the work of William Kermick and Anderson McKendrick, which looked at the modeling of the spread of infectious diseases. In fact, on one of our homework assignments, we discussed the modified model ds dt equals negative alpha times s times I plus gamma times r, di dt equals alpha times s times I minus beta times I, and dr dt equals beta times I minus gamma times r. Here, alpha, beta, and gamma are constants, whereas S denotes the percentage of a population that is susceptible to a disease. I denotes the percentage of the population that is currently infected by the disease. And R denotes the percentage of the population that once had the disease but is now recovered from it. You'll see here that in each of the boxes, we have a certain amount that is either leaving the box, moving to a different box, or this box is now being increased by a certain amount coming from a previous box. If we consider the basic reproduction number R0, which is alpha divided by beta, then we see that this three-dimensional system has exactly two equilibrium points. In the next lesson, in lesson 17, we focused on the work of Edward Lorenz to take a look at the following three-dimensional system. dx dt equals sigma times y minus x, dy dt equals rho times x minus y minus x times z, and dz dt equals negative beta times z plus x times y. In this case, this system has exactly three equilibrium points, and we call these Lorenz attractors. And finally, in lesson 25, we introduced the following three-dimensional linear system with constant coefficients. That is, dx dt equals alpha1 a11 times x plus a12 times y plus a13 times z, dy dt equals a21 times x plus a22 times y plus a23 times z, and dz dt equals a31 times x plus a32 times y plus a33 times z. We found that there is exactly one equilibrium point for this system if and only if the determinant of a certain 3 by 3 matrix does not equal to 0. Now that we've seen some examples of three-dimensional autonomous systems where we know something about its equilibrium points, we'd like to know, can we classify these equilibrium points as either saddles, sinks, sources, or spirals? To get an idea of how to answer this question, let's first review some ideas on how we classified equilibrium points for other types of systems. Let's start by considering a one-dimensional system, namely dy dt equals f of y. By considering a Taylor series expansion around an equilibrium point, say y sub 0, we find the following linearization. That is, let's consider a new variable u, which is y minus y0, so that du dt is equal to alpha times u. Here, alpha is f prime evaluated at our equilibrium point y sub 0. In lesson number 6, we found that the equilibrium point y sub 0 is a sink if f prime of y sub 0 is negative, a source if f prime of y sub 0 is positive, and that we're inconclusive with this information if f prime of y sub 0 equals to 0. We need a little bit more information before we can classify this equilibrium point as either a sink, a source, or perhaps even a node. Now let's consider a two-dimensional autonomous system. dx dt equals f of xy and dy dt equals g of xy. Let's now say that we have an equilibrium point corresponding to x0, y0. By looking at the ideas from lesson 31, we may consider a Taylor series expansion around this equilibrium point to find the following linearization. Now we have a new variable, let's call this capital Y, which consists of x minus x0, comma, y minus y0. In this case, we find the two-dimensional linear system dy dt equals capital A times y, where capital A is what's typically called the Jacobian matrix. For the moment, let's denote T as the trace of this matrix and D as the determinant of this matrix. We found in lesson 24 that we have an equilibrium point that is either a sink or a spiral sink if the trace t is negative and the determinant d is greater than or equal to 0. We have a source or a spiral source if t, the trace, is positive and the determinant d is greater than or equal to 0. And finally, we have a saddle if the determinant d is less than 0. We need a little bit more information to classify this equilibrium point if t is equal to 0. Recall that if t is equal to 0, and we know that the roots are complex, if that we know that we have complex eigenvalues, then we call this a center. Otherwise, we need a little bit more information before we can even call this a node. Now that we focused on what happens for one-dimensional systems and for two-dimensional systems, let's see what we can say about what happens for three-dimensional autonomous systems. Let's say that x0, y0, z0 is an equilibrium point. Then, just like before, we can use a Taylor series expansion to form a linearization. Here we'll introduce three new variables, u, which is x minus x0, v, which is y minus y0, and z, which is z minus w, which is z minus z0. Here we see that we can compute the derivative d by dt of the vector u, v, w to express things in terms of a 3 by 3 matrix. The coefficients of this 3 by 3 matrix can all be expressed in terms of partial derivatives evaluated at our equilibrium point. We have a motivating question now. How do we solve this three-dimensional linear system? Well, we discussed this a few lessons ago. First, let's observe that we can express everything as a product of matrices. Here, we'll consider capital A to be the 3 by 3 matrix you see on your screen. Recall that the trace and determinant of this 3 by 3 matrix are slightly complicated formulas. The trace is just the sum of the diagonal elements, whereas the determinant is a slightly more complicated expression involving the sum of three terms minus three more terms. Recall that we can compute the characteristic polynomial as the determinant of A minus lambda I3. I3 here is just the 3 by 3 identity matrix. We can express this as a cubic polynomial, lambda cubed plus p1 times lambda squared plus p2 times lambda plus p3. Here, p1 is just the trace of the matrix A, and p3 is negative the determinant of A. p2 is a little bit more complicated to express and cannot quite be expressed in terms of the trace and the determinant. We just mentioned in passing that the u, v, and w coordinates of this vector y satisfy a third-order differential equation. Conversely, if we're given a third-order differential equation, we can always express this as a three-dimensional constant linear equation, as you see here on your screen. The following proposition explains now how to actually find the solution for a three-dimensional linear equation. We have to take a look at the eigenvalues and eigenvectors of the matrix A. First, if A is diagonalizable, then it must have a basis of eigenvectors. In fact, this is the definition of being diagonalizable. In this case, the general solution to our three-dimensional system is just a linear combination of straight line solutions, namely y sub I is e to the lambda it times v sub I. Lambda I here is the eigenvalue, and v sub I is the eigenvector. On the other hand, if A is not diagonalizable, then we have two cases. First, say that there are just two distinct eigenvalues. This means that the characteristic polynomial factors as lambda minus lambda 1 squared times lambda minus lambda 2. In this case, we can find a basis, say v1, v2, and w1, where v1 and v2 are eigenvectors, and w1 is a generalized eigenvector. That is, a minus lambda I1, I3 times W1 equals V sub 1. Then the general solution in this case is a linear combination of two straight line solutions, namely e to the lambda 1t times V1, e to the lambda 2t times V2, and a third solution in the form e to the lambda 1t times the vector t minus V1 plus W1. Now, the second case is if there is only one eigenvalue. That is, the characteristic polynomial factors as lambda minus lambda 1 cubed. In this case, we can find a basis for R3 consisting of an eigenvector v1 and two generalized eigenvectors w1 and w2. In particular, a minus lambda 1 I3 times w1 equals v1, and a minus lambda 1 I3 times w2 equals w1. In this case, the general solution is a linear combination of three functions. The first two we've basically seen in the previous case, e to the lambda 1t times v1, and e to the lambda 1t times the vector t times v1 plus w1. The third function is a bit more complicated. It is e to the lambda 1t times the vector t squared over 2 times v1 plus t times w1 plus w2. This here gives us a complete solution on how we can find the general solution to our three-dimensional linear system. Let's end today's discussion by going over a couple of examples. First, let's say that we have the SIR model. Since we'll need to compute some partial derivatives, we'll do them here on the screen. This will help us to then compute the Jacobian matrix. Now, remember that in this case, there are just two equilibrium points, namely the point 1, 0, 0, and another slightly more complicated point that we're going to ignore for the moment. For the first point, namely 1, 0, 0, we can plug in x is 1, y is 0, and z is 0 to find the Jacobian matrix. And here on the screen now, we've computed eigenvalues and eigenvectors. Notice that lambda 1 is negative, whereas lambda 3 is positive. This means that we have three distinct real eigenvalues. And in fact, here on the screen, v1, v2, and v3 form a basis. So in this case, because one of the eigenvalues is negative and the other one is positive, we'll say that our equilibrium point 1, 0, 0 is a saddle. Now let's consider the Lorenz system. Just like before, we'll compute partial derivatives. Just like before, this will help us to figure out the Jacobian of our system. We also found in a previous lesson that this Lorenz system has three equilibrium points. Let's just focus on the origin, namely 0, 0, 0. Upon plugging in x is 0, y is 0, and z is 0 for the partial derivatives above, we can compute the eigenvalues and eigenvectors for this system. We then find that lambda 1 has to be negative, and the way that we've chosen tau, at least one of lambda 2 and lambda 3 is positive. Just like before, one of the eigenvalues is negative, the other is positive, hence we see that the origin 0, 0, 0 must indeed be a saddle. Thanks very much for watching.